In this example, we'll look at how solid edge simulation accommodates for the needs of our customers for analysis of their parts and assemblies when it comes to heat. We'll be testing this new audio amplifier to ensure that it meets consumer electronics standards when it comes to heat output, as well as look at how thermal expansion, or the expansion of material from the application of heat, might require a rethink on our original design. Before we get started setting up the simulation studies, let's simplify this assembly. Turning off unnecessary parts is a great way to cut time on the simulation analysis. Additionally, Solid Edge offers great tools to use on our parts to detach or turn off unnecessary features. Here, we simply select the features that aren't needed and tell Solid Edge to detach them. A simple way to remove unnecessary complexity that increases mesh time without losing the features themselves. Now that our assembly is simplified, let's get started on the simulation study. In order to be in compliance with consumer electronics standards, we need to make sure that the internal temperatures of the electronic components don't exceed a temperature of 70 degrees Celsius. Additionally, we want to make sure that all of the external surfaces fall below the temperature that is considered too hot to touch, which is around 44 degrees. Solid Edge offers a logical flow for providing the proper inputs for the steady-state heat transfer study. First, we'll set a body temperature, or starting temperature. Then, a temperature on the edges where the amplifier mounts. Each of these are set to an ambient temperature of 25 degrees. Next, heat generation occurs when power is provided to the circuit board. This particular amplifier has a power output rating of 250 watts. And finally, the casing is set up as a heat sink, designed to produce an optimized natural convection. Seeing as each fin will convect in all directions, we'll use Solid Edge's face selection filter and simply fin select the fins needed. A quick adjustment of ambient temperature for consistency, and our study is set up. Another great tool is the automatic connections command, automatically setting connectors between parts based on how they're placed in the assembly. A huge time saver, especially when working with multi-part studies. And finally, we'll mesh and solve. Solid Edge offers full control over our study mesh, the same as linear static and all other simulation studies. When meshing, Solid Edge is performing finite element analysis, or FEA. FEA is done by breaking up geometry into small nodes, or elements, that are measured based upon the input parameters of the study. For this study, Solid Edge is measuring the effect of the temperature inputs on each other to see how much heat is generated and how it moves throughout the assembly. As we look at the results of the study, we immediately see the maximum and minimum temperatures on the color bar. When looking at the results of an analysis, Solid Edge offers many great tools to ensure that all requirements are met. Our first requirement was to ensure that our internal components won't reach a temperature higher than 70 degrees. Turning on our maximum marker, we see that the board is well below that. Next, we need to make sure that the surfaces of the assembly don't exceed the 44 degrees that is considered too hot to touch. Using the probe tool allows us to get readings across the entire length of the casing. And as we take measurements, it's easy to see that we're well below our required temperature. You'll notice that our probe tool not only places information in the created boxes, but also in a spreadsheet collecting all of the information from each probe in the session. This makes reuse of this data a breeze for things such as design reviews. A simple copy and paste brings the information into Excel where we can use it however we see fit. Here, we'll simply create a temperature versus location chart of our findings. In addition to the temperatures along the casing, we also need to probe the lid to see the maximum temperature reached while in use. Another quick probe and we can see a maximum temperature of 31.1. The reason for finding the maximum temperature is so we know how the lid will react once heat is applied to it. This reaction is called thermal expansion. Thermal expansion is the swelling or enlarging of a material as heat is applied. This can lead to problems as stress gets placed on the mounting holes where the lid is held in place. To test for this, we'll set up a steady-state heat transfer study in conjunction with a linear static analysis. This not only shows the effect of heat on an object, but the resultant stresses from the thermal expansion as well. Since we know the maximum temperature placed on the lid is going to be 31.1 degrees, we'll simply round that up to 32 when placing the heat load. A quick fixed constraint on all of the holes, and we're ready to mesh and solve. Using mixed studies like this is another way in which Solid Edge helps to ensure that our designs are not only built correctly, but that they'll work as intended when produced. As we look at the results, the lid seems to have a large amount of deformation taking place. Not to worry, this is Solid Edge simulation showing you an exaggerated view of how the part will react. Clicking on the actual deformation, we can see that heavy stresses are placed on our holes, as we expected. Additionally, we can also see that the resultant stresses are well over the yield stress of our current aluminum material. Good thing we ran an analysis, because it looks like it's time to make some changes. Solid Edge provides us with a large library of materials to pick and choose from that is easily customizable with any materials that we commonly use. Here, we need a stronger aluminum to be able to withstand the stress of the thermal expansion, so we'll pick this 6061, a common aluminum alloy that is considerably stronger. Of course, with the simulation study already set up, all we need to do is resolve in order to test and ensure that our new material works. The simulation results show the same overall stresses being placed on the lid, but the new material has a much higher yield stress that won't be at risk of deforming around the holes. Now that we're confident that the amplifier will not only meet our consumer electronics requirements, but also work as intended under a heat load, it's time to create a report to show all of our results. As seen in other simulation examples, automated report generation is easy in Solid Edge. Simply click Create Report, fill out the necessary information, and choose what format you want to display it in, from a Word document to a web page. As you can see, it doesn't matter what types of studies you're running. Solid Edge simulation provides its users with a quick and consistent experience that saves time and money, showing design engineers where problems are likely to occur well before the parts are physically built. And rest easy knowing that Solid Edge simulation leverages FEMAP and Nastran, world-renowned simulation technology ensuring accurate results. Solid Edge, design better.